It's a bit odd that I can't see any of you, but I'll assume that everything is fine. Hi, so I'm Aishwarya. I am an assistant professor at University of Montreal and Mila. So I'm right now joining from Montreal. It's 6:30 a.m. my time. And I wish I could be here in person, but yeah, the travel plans didn't work out. All right, so I'll be in this part of the tutorial. I'll be talking about connecting vision with language, learning from language, and just vision language applications as well. So let's get started. Um, right. So I would like to connect. I would like to start my talk from this clip model, and I'm sure you have seen this already in some of the previous talks. So the idea behind clip was how to generalize from a fixed set of we are doing image classification, and how do we go beyond this fixed set of image classes or image labels, right? And what they proposed here is instead of training for a fixed number of classes, what if you could cast this problem as an image text matching problem, right? So this problem of image text matching is not new. In the vision and language literature, it has been existing for quite a while. But the promise of this paper was to show that you can really learn very strong image recognition models by just learning from language, right? So basically, yeah, once you have converted every label into a text at inference time, all you need to do is just compute the probability of which text has the highest matching score with the image, right? And so here the text is very simple. It's just converting every label into a templated sentence, a photo of plane, photo of car, and so on, right? So this you can call this a vision and language model. I don't really like to call it that. It's essentially a visual recognition model, which is learned from language. It's a basic model in terms of its language understanding capabilities, right? So you can do image text matching, and if you actually play a lot with this model, you will figure out that it is not really capable of understanding the structure of the language quite well. So it is quite sensitive to the presence of nouns. So it is very good at detecting what are the nouns in the sentences. But if you change the order of the words, or if you test its understanding for more complicated sentence understanding like adjectives, adverbs, and it's not very good at that. So that's why I don't like to call it a vision and language model. To me, it's just a vision model. So where I want to go from this is, sure, so you have this clip model, which has some sort of language understanding, and you can do image text matching with this. And it tells you a bit about the power of connecting language with vision, but it cannot go beyond image text matching, right? It cannot go beyond image classification. But what if you wanted to do image captioning, right? What if you wanted to generate captions for images, or you wanted to do visual question answering, or like image retrieval, where you would want to retrieve images based on more fine-grained differences, such as man with a black and yellow tie, and so on. And what if you wanted to do image generation condition on language altogether, right? So just by connecting language with vision, you can do a lot more interesting things than just image classification or image text matching, as we were doing in clip, right? Um, so basically, I want to talk about, in this talk, I want to talk about these BQ image captioning types of tasks, and I want to tell you what are the kinds of models we are using, what are the kinds of sort of the state-of-the-art models that we're using these days. And then finally, I want to conclude with what are the challenges still in vision and language, right? It's not like by connecting vision with language, we have solved a lot of, I mean, there are a lot of outstanding challenges here as well. So, but before we get started, I would just like to motivate vision and language a bit. So, as a vision and language, by connecting language with vision, you can now use these systems for different applications. So for example, it can be used to aid visually impaired users. So visually impaired user can now interact with the vision system in natural language, which is for humans, language is a very natural and easy form of communication, right? So if I have access to language, I can directly ask what kind of wine is this, what temperature is my oven set to, and things like that. So from an application perspective, it makes it quite easy. Similarly, for online shopping and organizing photos, having access to a language interface, I can query this, let's say, a photo app with advanced queries, asking for like, find me photos when I was wearing a pink jacket and I was on top of a mountain, and so on, right? So it just gives me more flexibility in the kinds of queries I can ask. And you can also imagine vision and language systems can enable you to have grounded virtual assistants. So having an assistant like Alexa, but which is visually grounded, right? So what if I could ask my Alexa if it had access to the visual system, queries like, have you seen my keys, or have you seen my laptop charger, and things like that. And in terms of the current state of research in vision and language, this is a qualitative example from the DeepMind's Flamingo model, which quite a few might have heard of already. And I'll talk a little bit about it in the later slides as well. So I just wanted to give you a flavor of what we can do at this point already in the field of vision and language. So here the model is prompted with an image, the image of the dog, and it starts off by generating a caption. So the text in pink is the text generated by the model, and the text in gray is queries asked by humans. So the model starts off by explaining this image. This is a dog, it's a white fluffy dog. And then we can ask, what season is this? The model says it looks like a summer day. Why do you think so? Because the grass is green and the dog is not wearing a sweater. So you see, in addition to understanding the contents of the image, it seems to have some sort of common sense reasoning, if you will. The dog is not wearing a sweater, and hence it's a summer day. What breed is the dog? It's Samoyed. Is the dog running? No, it's sitting. Can you describe the pose of its back legs? The back legs are bent and the dog is sitting on its haunches. So this, to me at least, this is pretty impressive in terms of the different types of questions it can answer, and it can understand the contents of the image. It seems to be showing some sort of common sense reasoning as well. And it's not the case that this has been possible just now with these latest models. Like in the vision and language community, we have been working on problems like VQA image captioning for a while, and recent models have become quite impressive. So it's quite exciting. And I'm sure you have seen image generation models as well, which are conditioned on text. So again, like connecting vision with language gives you this flexibility to generate different kinds of images with different compositions of concepts, such as a dolphin in an astronaut suit on Saturn. So even though we don't see dolphins in astronaut suit near Saturn, the compositionality aspect of language, that we can compose different words together and ask for completely new concepts, it gives us this facility to query our generative vision generative models to generate these kinds of images. So it's pretty impressive. It's pretty exciting, the current state of vision and language research and the kinds of um, outputs we see out of these models. That is pretty exciting for sure. Um, and like as I said, like all of this excitement that we are seeing recently, it's not coming out of nowhere, right? So there has been a long history of vision and language research, and a lot of progress we have made in the community. So this is a plot of the performance of models over the years on the VQA V2 dataset. So this is one of the most popular VQA datasets used for benchmarking models. And I used to organize this challenge every year with my colleagues at CVPR. So we started doing it in 2016, and then 2021 we reached very close to the human performance already on this dataset. So we stopped doing the challenge. And today, the performance of, I think, the state of the art model, which is beyond human performance, is this Pali model from Google. Um, I just checked. I think this particular model was uploaded just 6 months ago, and Flamingo model, whose outputs I was showing earlier, that's also surpassing human performance. But basically, it took, so all of this started around 2015, and with 2023 now, so it has been 8 years, and the progress is huge. You can see 31% improvement in the performance compared to the baseline model we released in ICCV 2015. Um, and in terms of the quality of models, in terms of the architectures, in the early days before transformers, the kinds of architectures we used to have was like CNN LSTM kind of architecture, which would basically be trained specifically on this data set. So very basic IID training and testing settings. And then with transformers, we are now in this era of pre-training and then either fine tuning or zero shot learning. And more recently, the models that are coming out, which are state of the art, are based on large language models, as you can imagine. So they are generative models and also based on large language models, and hence they possess this zero shot and few shot capabilities. So basically, there has been a lot of progress, which is quite exciting, right? Yeah, so let's take basically a quick tour of this progress in terms of the evolution of models. So this is how a typical VQM model used to look like before the era of pre-training and transformers. So we would basically given an image and given a question such as how many horses are in the image. We would extract visual features using usually a pre-trained visual encoder like a ResNet or some sort of pre-trained CNN. And the question features would be extracted using a learned question encoder, so like an LSTM model, which we would learn along with using the VQ loss function here. And then there would be a third component, which would basically be combining the visual features with the language features. And this could be as simple as point-wise multiplication between the vision and language vectors, or it could be attention-based module as well. So, we were doing cross-modal attention even before transformers came out. Um, and typically, the way we would treat this problem would be as a classification problem, where we are producing a probability distribution over some predefined set of answer classes, which are usually mined from the training data set. So, yeah, but basically, this model would be trained for the task of VQ only, trained on the training set of whatever data we are planning to evaluate the model on. And then starting 2019, the summer of 2019 was saw a lot of excitement because that's when NLP started seeing a lot of progress with BERT style models. And naturally, the vision and language community started applying those ideas to vision and language as well. So basically, then we saw a shift in the kind of models we would build, and the kind of models we would build would be centered around transformer-based models, and they would have this pre-training and then fine-tuning notion. So the pre-training would be performed, and even today, like this is a very common pattern. So if you look at good state vision and language models, they would be pre-trained on image caption paired data. So this pre-training requires access to paired image and caption data. And there is, if you wanted to think about the type of the pre-training data, you can roughly divide it into two categories based on whether the captions are written by humans or whether they are coming from the wild internet. So MS Coco is a very popular image caption data set, and it has driven a lot of progress in image captioning and also VQA. So here the captions you can see they are written by humans. They are very good in quality and are very descriptive. They're faithful to the images. So basically these captions are talking about concepts in the image. And then more recently, MS Coco open images narrative data sets has come out. So this is also manually annotated, and it is much more descriptive about the image. Visual genome is another important data set. The unique property of this data set is it has bounding box annotations in the image, and you have phrase descriptions for each bounding box. So you have basically region descriptions here. On the other hand, we have data sets which are much larger in size because they are scraped from internet. They're not manually annotated. So these are conceptual captions data set, and SPU captions are two examples. I think there are many more like Leon recently. So conceptual captions is essentially these are the images, and then the text is basically the all text field corresponding to these images on the web pages from where these images are mined. So these captions there's much more diversity and they are mined from internet. They're much larger in size, but you might see that they're not necessarily describing the visual element. Sometimes they talk about the context around it. So, for example, here the scenic route through mountain ranges includes these unbelievably colored mountains, right? So its quality, it's a bit different compared to like Coco kind of data set where the human is explicitly asked to describe the visual elements in the image, and here they might talk about like more abstract concepts as well. Similarly, this SBU captions data set has named entities like King Arthur's name of uh, uh, yeah, proper nouns and things like that. So quality wise, they tend not to be that great, but they are much larger in size. So there is always this trade-off. Okay, so we are talking about these models which are, transformer based, and they usually involve some pre-training and then fine tuning or zero shot learning. So basically, here I'm talking about dual encoder kind of models. So these are the first models that came out around 2019, 2020 when the field shifted to using transformers and pre-training based methods. So an example of this method is the Wilbert model. That was, I think, one of the first models that came out. So basically, these kinds of models, typically what they involve is they would involve some sort of multimodal transformer. Either it can be a single transformer that takes both images and language as input, or it can be two separate transformers, one for image, one for language, with some cross attention in between. And typically, then what we do is in the pre-training stage, so we have images and captions. So we would take the captions and tokenize them either at the word level or sub-word level, and then mask some of these words because we are trying to do mask language modeling here. On the image side, the tokenization takes place at the level of bounding. So different papers do it differently, but a common approach is extract, basically given an image, run it through an object detector, extract what are the objects and what are the features corresponding to these objects. So what we are feeding here are essentially different object level features. And then we have different types of losses. So we have masked language modeling loss, trying to predict the masked word in the caption. There is masked image modeling loss as well. So here we are not actually trying to predict the missing pixels, but here we are trying to predict, let's say, doing feature regression. So trying to regress to the features of the like the missing object here. And there is cross-modal loss, which is typically matching loss. So trying to predict whether this caption and given image match with each other or not. And more recently, we have started using contrastive loss inspired by Clip for this particular image text matching head. So for all these three losses, there is interaction between vision and language. So you're learning this joint representation, which is visual linguistic representation. So that was the pre-training stage. And then typically there is a fine-tuning stage with these models, which is where we use different heads for the different downstream tasks. So for the VQA task, the way it is set up is you take the image text matching head, and then you just add a classifier over the vocabulary of answers, and we fine tune with this on the VQ dataset. And typically, the whole model is fine tuned when we're doing the fine tuning. So, yeah, as I said, an example, this is one of the early examples of this family of model, which is pre-training and fine-tuning with these discriminative or like image text matching head would be Wilbert. And Wilbert, this paper used basically um, two separate transformers, one for vision, one for caption, and then they would be cross attention at, I think, few different levels. Um, uh, there are also, you can also think of encoder decoder kind of setups. So the setup I described previously, right? This setup, this cannot generate caption. There is no decoder here. So it's just encoder only model. It can do tasks like VQA, image text matching, but if you wanted to also have image captioning included as one of the tasks, then there are papers that essentially the encoder setup is quite similar. So you have image and caption as input, and you model it using a joint encoder, and then you stick a decoder on top, right? And this decoder is typically a decoder transformer. And now the whole network is trained with language modeling laws, so image captioning laws, essentially. And I've listed some example papers here, which were early examples of this kind of family of models. And these papers that I've listed here, they would typically start with some sort of a pre-initialized language decoder. So this would be some language model like BART or T5. And then with the image captioning laws, the encoder and the decoder, both of them would be updated and learned, right? So this would again fall in this regime of fine tuning. So once we do the pre-training, and then we um, depending on which image captioning data set we are interested in evaluating, then we would fine tune. So all these models that I described until now, the common property would with all these models was there would be a pre-training stage where we are trying to make use of pre-trained language models, but also generally large image caption data sets and learning from them. But there would always be this fine-tuning stage, right? So whatever data set we are evaluating on, we would fine-tune on the training split of that data set. Um, However, more recently, this again, there has been a shift in the vision and language community, and we are starting to see models which are based on large language models, and that basically gives the ability to our vision and language models to be able to do zero and few shot prompting. So here I'm highlighting a common skeleton for a bunch of these models that are coming out recently. There are many, many models that are coming out every day. It's hard to keep track. So the common flavor they have is they make use of some sort of pre-trained large strong visual encoder, and typically this is clip kind of visual encoder, which has good out of distribution generalization capabilities. And then there would be a pre-trained large language model of the size of, GPT-3, Llama, and these kinds of models. And basically, so they take these pre-trained vision model, pre-trained language model, which are already individually very strong for unimodal generalization. And then there would be this orange arrow here you see is what we call mapping network. So there would be this mapping network that would be learned, which would be trying to connect the vision part to the language part. So typically the vision encoder gives you these features for images and like grid-based features and so on. And then the idea is to feed those to the language model. So you need to um, uh, adapt these features so that the language model can consume these features, and we need to adapt it to the input space of the language model. So that is where a typical mapping network would be involved, and this mapping network can be as simple as a linear layer. So there's one paper that tries doing this adaptation using linear layer, or as complicated as a big transformer. Yeah, so there are a bunch of different methods that fall in this high level overall family. So these are some early papers that were published at ACL 2022. What they do is when they do this, so by the way, this mapping network would be learned on, again, image captioning tasks. So we'll feed the image and to the vision encoder, extract features, map it through the mapping network, feed it to the language model, and then the language model would generate the caption for the image. And then we have supervised data for that, these large image caption data sets. And then we would basically train either just the mapping network or adapt the language model as well, and also adapt the vision model. So it depends which component you are adapting. But the overall pipeline is the same. We are just training this mapping network using image captioning model, image captioning laws. So some of these papers here, they would essentially just fine tune the entire language model. So the language model those days would not be as big. I think they were still using maybe T5 kind of models. And that essentially we're fine tuning the entire language model. It gives you good performance for the vision and language tasks, but then it's not very, it might not retain a lot of the power of the language model. There are other papers like Flamingo that I talked about. Magma is another example. What they would do is they would insert adapter layers in the language model, so you're not fine tuning the whole language model. There was this paper Frozen that came out very early on. What they tried to do is initialize the vision encoder from scratch and then learn to adapt the vision encoder to the input space of language model, right? So here we're not touching the language model. The language model is frozen, hence the name of the paper Frozen. And then we are just adapting the visual encoder to suit to the language model. We also published a paper in this space called Maple, where we only learned the mapping network, and we had a small transformer as a mapping network. You might have heard of this Blip2 paper that has become very widely used these days. And they also fall in this family where they only learn the mapping network. They have a more sort of a bigger mapping network and a two-stage pre-training and so on. But yeah, so most of the vision and language models that are very recent and state of the art typically follow this kind of high level architecture, if you will, where the idea is to make use of large language models essentially. And yeah, so these methods that I listed here, the trade-off usually is parameter count versus performance. So if you're fine-tuning the language model also, then your performance is much better, versus if you are just training the mapping network, the performance is worse, but you save a lot of parameters. Right, so another thing I wanted to mention here is these methods, because they are making use of large language models, they are capable of prompting. So you can basically uh, you can basically evaluate these models in a zero shot or a few shot prompting settings. So as I said, these are trained only on the task of image captioning. Now at test time, we can evaluate it for VQA or other tasks as well. Even though these models have never seen any kind of VQA data, because now they can do learn new tasks by prompting, because they are making use of large language models. We can teach them new tasks at test time, right? So that basically just by the virtue of using large language models, we can now adapt them to new tasks with just few examples. Right, so that covers, a very quick overview of where we stand in vision and language right now. And in the next 10 minutes or so, I would basically like to highlight where are we going next, right? So it is quite impressive, the progress we have made until this point. And by connecting language to vision, we can we're no longer limited to this fixed set of labels that we can generalize over. We can generalize to the full language space. You can generate captions, answer questions, and so on. But there are still a few different challenges that come along with vision and language. And are you saying something, Taylor?
Nope, nope.
Okay, sorry. How much time do I have, by the way?
We're running quite over, so probably a couple more minutes, and then Mossy will give the conclusion.
Oh, okay. So yeah, I'll be very quick then. Right. So let's see. So when I say out of distribution generalization, what I mean is with these, large vision and language models, you might imagine that because they make use of these LLMs, they are capable of zero-shot generalization and few-shot generalization based on prompting. This is all true, but the performance is not as great. So if you care about, let's say, performance on a particular task, let's say a VQA task, the best scenario to get highest performance is when you fine tune the model for that particular task. And once you fine tune the model for that particular task, then that model becomes very specific, specialized to that task, and not just that task, to the data distribution for that task. So if you basically, when I say out of distribution generalization, what I'm saying is when you fine tune these vision and language models on one data set, they are not very good at generalizing to another data set of the same task. So I'll briefly highlight this paper of ours that was published at ESCL findings this year. Here we took Wilbert and Albef, those were the state-of-the-art models at that time, and we basically fine-tuned it on one VQA data set at a time and evaluated them on a different VQA data set. And we essentially saw huge drops in the performance in the OOD generalization. So, in spite of being pre-trained on these large image caption data sets, one would expect that these models would learn some general purpose VQA features, but they in fact tend to learn, they tend to overfit to the format of the question, tend to overfit to the answer priors, and so on. So these are still some of the things that we need to improve upon. Another important challenge, which is much more widespread, is this challenge of compositional reasoning, visual linguistic compositional reasoning. And you might have seen this ground data set, where the idea is to predict the right match between the image and the caption. And the unique property here is the captions consist of the same words. They only differ in the arrangement of these words, right? So light bulb surrounding some plant versus some plant surrounding a light bulb. So the model really needs to understand the structure of the language, but not only that, it needs to match it to the corresponding image, right? So language models are very good at compositional understanding when it's only about unimodal language only compositional understanding. But here we are talking about visual linguistic compositional reasoning, right? So they also need to understand the corresponding elements, the bulbs and the light, and the arrangement of whether the light is outside, the bulb is outside, sorry, the leaves are outside or the bulb is outside, in the image, in the language, and make the corresponding match. And till date, this is one of the hardest challenges, in my opinion, for vision and language models. There are a bunch of other data sets that were proposed for evaluating the same kind of thing. And a lot of these models, which are at least based on clip kind of model, because this is image text matching task, what they do is create hard negative. So you create hard negative sentences and essentially ask the model to differentiate between hard negatives, right? So that you're trying to improve the fine grained understanding capability of this model by distinguishing hard negative sentences from positive sentences. We also have a recent archive submission in this space where in addition to hard negative, we implemented two more losses. So we are also trying to do contrastive loss between the hard negative text and the positive text. And we are trying to enforce rank loss. So some minimum margin between the positive image text pair and the negative image text pair. And we also have a curriculum learning here. So as the training progresses, we make the margin bigger and bigger. So we make the learning problem for the model more and more difficult. And we show we improve the performance on some of these recent data sets. So yeah, but basically compositional reasoning is still quite a bit of challenge, and it is becoming better with these models that use decoder kind of models, so language models, but still we are not quite there yet. The last thing I want to highlight is evaluation, right? So here we are talking about language models, so we are generating language. Evaluating language is not easy. So when we talk about image captioning, here we have to evaluate whether the generated caption is correct with respect to a given image or not. Previous approaches used to do this matching, n-gram matching between the generated caption and the set of ground truth captions. more recently, this CLIP score, this is a screenshot from the CLIP score paper where they essentially propose using the CLIP model directly to compute image text matching score between the generated caption and the given image. One of my students, we did this analysis and we found that essentially even this CLIP matching is not very robust. It fails to recognize fine grained differences. So here, it is giving higher score to the caption title of the book is muffin compared to the correct caption title of the book is topology, because muffin is a concept which is present in the image. So it's giving higher score because of that, but it doesn't really understand the structure of the language here. And we also show that this kind of metric is bad at understanding negation. It is biased by the length of captions and so on. And we did some more analysis showing that it is quite sensitive to, so if you have more number of object mentions in the caption, or you have mentions of bigger objects compared to smaller objects, you get higher score, which is a bit counterintuitive. And if you shuffle the sentence, it doesn't really matter much. Anyway, so this is the last thing I want to point out is like same applies for VQA evaluation as well. So until now, for VQA evaluation, we used to use this string matching between the generated answer and the ground truth answer. And because the answers used to be very short, typically one word, the string matching would work quite well. But nowadays we are using these zero shot models, and we are doing out of distribution evaluation. So the space of answers that are generated by the model need not match the space of ground truth answers, right? The model has not been optimized for ground truth answers. So the answers tend to be, the string matching fails now. And we submitted a paper to AAAI recently where we are proposing using large language models as evaluation metric. And we show that you achieve much better correlation with human judgment compared to string matching. So with that, I would like to conclude, and basically I would say just two things, that connecting vision with language gives you much more freedom in terms of the kinds of things you can do, and also freedom in terms of the space of concepts you can generalize to. So it definitely makes the models more generalizable. But there's still quite of challenges with vision and language, and I highlighted some of the challenges that are very near and dear to me, like compositionality, OD, and evaluation. So there's a lot of room for improvement here as well. So thank you so much for listening, and happy to take questions.
Thank you so much.